what I'm going to do is explain again like a bit of what autoencoders are. So AE or autoencoders. As I mentioned before, these are networks, right? Machine learning networks that we can code using the Keras sequential API using TensorFlow and any type of machine learning library. I'm going to try to explain to you what I've learned before, and maybe out of this we get some content that gives you a hint of what these networks or this type of code might be useful for. So an autoencoder means that we have an image, and if we go back one step. Hi everyone, it's Nono here, and this is an overview on autoencoders. I want to emphasize the importance of the word auto here. Auto means that whatever inputs we're feeding into the networks, we have a set of things that we're feeding into a neural network that then will spit something, autoencodes. So we don't have to label the data. It's an unsupervised machine learning algorithm. So that's, I think, where the auto comes from. Right? We don't have to do anything for the network to learn what's called decoding. So let's get back. So we have that auto there. What an autoencoder will try to do is get an image, right? So let's say we have an image of a landscape, the sun, and the tree. And even if it sounds a bit weird, what we want the autoencoder to do for us is go into a neural network, right? So an algorithm that takes some parameters and then outputs at the other end an output. And we actually just would like, the ideal thing would be that the autoencoder brings back the exact same image. That sounds a bit weird. To me, this sounds a bit useless. If I already have the image and I want a network that just returns exactly the same image as precisely as possible. All right, so there is a story here, right? This is the gist of, or like the overall way of seeing this. But what is actually happening is that when we have that initial image for a tree with the sun, with the landscape, we put it into a network, right? This is what's called an encoder that produces, so for this image that, I don't know, maybe it's 28 by 28, or maybe it's 256 by 256, whatever amount of pixels you want, it's actually going to generate something called the codings. You can think of codings as another image, maybe black and white, doesn't need to have RGB channels, that has less information, less pixels. So maybe we have a codings that are, I don't know, like maybe 5 by 5 pixels or something. So that would be, we have 25 digits per image. And that is like a simplification. We have an image and this was, let's say, 28 pixels inside. And then what we're doing is we're making it go up to 5 by 5. So you would go from something that is bigger, has more detail, into something that is smaller, right? So let's zoom in into here for a second. So we're going from 28 to 5. From something big to something small. And actually, you don't even need to think about the codings as something like this. It doesn't need to be a square by square. It can be, as we saw on a previous video on the flattened layer, it could be just a series of zeros and ones that are one after the other, representing maybe like 0, 1, 0, 1, 0, 0, 0, 1. And each of these numbers or series of numbers that maybe has like 20, 25, or I don't know, let's say 30 digits. It's encoding the knowledge that the network has learned for your original image. All right. So going back once again to the original concept, what we were trying to understand. So we go from this image into an encoder, and that encoder gives us what's called a coding, right? So this is a coding. And there are a series of layers inside of here that represent the network that we're using. And again, what we have here are called codings. And after we have those codings, let's say it's like compressing data, because we have, if we multiply that, so 256 by 256, that might be 65,000 pixels, that then will have 3 RGB values per pixel. Here we just have 25 digits. It's like a really small amount of numbers. So here we go from point A, that is an image, to point B that are our codings. We could save our images as the coding that we have there. And where do we go next? So the same way we have an encoder, we have another piece that is a decoder. What the encoder does is it grabs some piece of information and then it codes it, something that has been coded, right? The codings. And then we get those codings, we feed them into a decoder, and then we decode them into something that hopefully looks like the original image. But just to represent here, maybe we get a moon instead of a sun, and maybe we get a few branches of our tree missing, because the network tries to generalize. So it tries to generalize how to generate new synthetic images from our codings. It doesn't know how to retrieve the exact original image. And if it did, it would be overfitting. It means that the network will only work for the codings that it knows about. But when it finds new codings, it wouldn't know how to generalize and synthesize another image. Okay, so yeah, we get image A in here, then we get the codings, and then we get the decoded image. Why would you want to use this? So these networks have proven not to be effective to compress data. As I mentioned before, JPEG, for instance, is a deterministic algorithm that seems to work a lot better for this purpose. But this has proven, for instance, good to do noise removal in images, or even filling in blank parts of images. That is because it actually reconstructs the image on the right with pretty low amount of information, the things that we get on the codings on the left. I'll remind you to like the video if you want to support the channel and the work that I'm doing here with these videos, and to subscribe if you want to get notified when I upload new videos or when I go live next. It's my pleasure to have you online, to have you collaborate and be part of the community. You can join None of the Maslas Discord. Thanks a lot for watching once again. I'll see you next time.